Yeah,
That's on
that is something you have to pay attention to, is that if you're not dealing with something purely quantitative and there was any sort of subjectiveness in it, that subjectiveness among these were the parameters, this is the result, are going to inherently go into the system you're creating.
Hello, everyone, and welcome to the Modern Web Podcast. I am your host, Rob Osell. I'm an architect at This.Labs. Today, we're very excited to sit down and talk neural networks with Chris Gardner. Chris is a products and platforms engineering manager for Accenture, the chairman of the DevSpace Technical Conference, a Twitch affiliate, and honestly, I could keep going. Chris, how are you doing today?
I'm doing wonderful. How are you?
I'm doing great. As of the time that we're recording this, we are both in the American South, and it is close to Christmas. At least it's supposed to be. It is exceedingly warm. So it is far warmer than it needs to be right
Yeah,
now.
it is fall temperatures right now for the South, not winter temperatures.
Listen, my family's in Minnesota, and I keep getting messages. They're all very sad. My sister just had her first birthday with no snow that she can even remember. They're about to not have a white Christmas. That's not a thing that happens in America's North. So it's a toasty year this year.
Yes.
All right. But that's not why we're here. We're here to talk about neural networks. And so I just think in this day and age, with so much attention being placed on large language models and generative AI, and people just really kind of becoming aware, maybe for the first time, or really focusing for the first time on sort of data science, machine learning, neural networks, and so on, that we needed to have this conversation. So for the people that maybe are not really engaged with this very much, and they just sort of put these all in the same bucket, can you help them understand like what a neural network is and how that maybe compares or contrasts to the things that they may have heard, like machine learning or AI or ChatGPT?
Sure. I'll first start with my soapbox, so to speak, of the differences between AI and machine learning, because they are two distinct things that occasionally overlap. Machine learning is the process of not knowing how to solve a problem, giving the parameters to some sort of program, letting it get incorrect answers, learn from those incorrect answers, and come up with a solution to where it can eventually solve the problem, but you don't know how it does it. So it is, and a large part of what neural networks are machine learning. So it is, here are the parameters I think that are relevant. Here's something to start on. No, you're wrong. Here's how wrong you are. Repeat until you figure out the answer, but then I can look at what you're doing to get the answer, and I have no clue what you're doing. So that's machine learning. Artificial intelligence is the process of giving a machine human-like aspects in such a way that it behaves naturally to how a human would expect. So you can see how between the two there's some overlap, but they're technically doing different things. And it's splitting hair and being pedantic and being academic at this point, but there is that distinction there. When you start talking about neural networks, they're technically referred to as artificial neural network. And the reason being is because the concept started way back, don't quote me on the exact decade, but it was like the 50s or 60s or when they first started playing around with it, when neuroscientists really started to understand how the neural networks and neurons in your brain worked. And some computer engineers tried to emulate that using programming techniques. They did not gain a lot of traction at the time because hardware was not powerful enough to deal with that sort of computing power. So they kind of fell into the wayside for years and years. And then probably about in the 80s, they kind of got picked back up as computers were then able to come together in ways that could reasonably, in small ways, approach those problems. And they started looking at the concept again. And then, especially when you get into the late 90s and the 2000s, when they quit trying to make things as powerful as possible and realized the true benefit of parallel processing, then that's when the whole concept and what we now know as neural networks really took off, because the computers and the hardware were finally at a place to tackle that problem naturally in a way it really occurs.
So it's probably not super relevant, but if we go back to kind of, you had this contrast between some of the differences in machine learning and AI, is it one of those classic sort of 3-circle Venn diagrams where neural networks are then fully another sort of intersecting entity, or where does it fit then onto this sort of gradient that you were positing between some of these different approaches?
Neural networks
really
would
just
be
kind of not important.
Yeah, well, it's not important, but neural networks would be a subset of machine learning. So it
That makes
is,
sense.
we are setting up the problem to the machine with generic, we don't even know if it'll work data, seeing how wrong it gets, retraining it based on telling it how wrong it was until it got the answer right. And typically the outputs, the pure inputs and outputs you get out of a neural network are generally in no way human usable. So we're
Mm-hmm.
purely out of the realm of artificial intelligence at that point. However, most systems you think about that are using it behind the scenes, classic examples in generative AI being ChatGPT and even Cortana. I know for a fact Cortana was a neural network. Is you have these AI layers on either side that are taking the input in nice ways and doing the transforms to make it to where all the machine learning can happen. It crunches the problem and then it takes that result and presents it nicely to the user as the first and last layers, so to speak.
So we're going to dive into more of the details on kind of how it works, but I think it'd be interesting to also hear why you got interested in this. I know you give talks on this, and that's part of the reason why we're talking about this. Is you have a really cool talk about explaining the basics of neural networks. You attempt to do it in an hour. We have much less than that here, but
Right.
so we're maybe setting
And I have visual aids and programming guides and pre-written code.
yeah, exactly. We got a very complicated speed run going on here. But so, as far as your history with neural networks, what led you to be interested in this and have this be a topic that you like to teach other people?
I had heard of neural networks previously before we get into all the other stuff, but coming through the educational system, I was always fascinated with AI. And I mean, it may come from Star Trek and data and science fiction and whatnot, but I was always interested in AI and kind of wanted to move my type of research that way. So when I was coming through college, I eventually ended up having the opportunity to take to get my master's degree. And it was supposed to be it was supposed to purely be Masters of Science in Artificial Intelligence. Due to a hiccup, and I'm not going to throw the school under the bus. I know exactly what happened. But due to a hiccup, it ended up not being that exact degree. It ended up being a Master's of Science in Computer Science with an artificial intelligence emphasis because one class just we couldn't make exist for the actual program. Long story short, I would have ended up in school for 2 more years to fake it. I said, nope, just give me the other one. Um, but and so that's where it came from. And then I don't want to say I sat on it for years, but I played around with the topics and curiosity led to certain things. And then as things like Cortana and then later the GPTs started becoming more prevalent, and I also started seeing within the industry that these wonderful libraries were being created. One of the original prototypes, I'm a .NET guy. One of the original prototypes was done by my good friend Seth Juarez, which was ML.NET, which is what became the basis of what the ML library for .NET in general is right now. And people were starting to really use these libraries and use a lot of the functions that were in them to do things. It kind of bothered me because of the type of programmer I am, and maybe it's the academic side of me, that I understand abstractions, but they were using these things and having no clue how they were working. And so I wanted to come forward and say, hey, it's not that you shouldn't use these libraries, because there's a lot of grunt work involved with playing around with these things that you really don't need to deal with. Having said that, this is all that's going on behind the scenes, and I wanted to present it and present the math and the elegance of it and going, here's what's going on, with the idea of if people understand what's going on behind the scenes, maybe it will help them when they're figuring out what type of data they want to use, how to present it, how to train it more efficiently, things like that. And it can just help people move on. Plus, by writing it, I produced a template where people could easily play around with small problems and really see things that the libraries won't let you see and play around with the nitty gritties of.
Yeah, and honestly, there's just a lot of vendors now between Apple, Google, and Microsoft and more that are making these tools sort of widely available and almost too easy to create. We were playing around with the iOS one recently, and it's just like, what do you want to do? You want to classify images? You want to do this? And I think it's probably right that it's good for people to have a basic understanding of what's going on under the hood. I mean, not to revive the old, like, should you use an IDE or should you just write in, or not an IDE, excuse me, a sort of a WYSIWYG visual editor tool, or just should you code in a notepad type of thing. But sometimes, in order for those to be really effective using those tools, it is good to understand how roughly how that's going to translate under the hood, even if you couldn't create the exact same model that it's going to help you create.
Right. And it goes back into, if I go back into an academic sense for a moment, just about every, at least undergrad program, will teach a course in uh, data structures. Simple things like linked lists and trees and arrays and stuff like that, that none of us care about anymore at all. You have to be a very specific place, like doing low level, really embedded or like microcontroller type work to actually care about how to implement one of those by hands, because we have libraries that do it all. However, spending the academic exercise of a week or two just talking about how it actually works, just so that your brain can think in those ways, can then help in other ways. So this is just another matter of, hey, let's take this complex problem that we now have libraries, which are 100% what you're going to use, unless you're the person writing the library, to solve these problems. But let's go through the exercise for a moment of explaining how it works and letting you see a little bit behind the covers, so that maybe you're never going to implement one, but maybe one thing it does then makes you go, but I remember this thing does that. Let's kind of glance at this and maybe this can solve our other problem. And I think a lot of computer science in general compounds on top of itself that way, to where I'm saying nothing against boot camp people, and that we need those, but we also need the people who have that intellectual curiosity to go, but why? And get to that next level so that we can continue having innovation as we go. And it's just helping fuel that.
Absolutely. So, last thing before we dive deep into the details here, but what are the types of problems? Like, when do you find yourself thinking to reach for a tool like this? Are there particular classes of problems? Because again, with the generative AI craze and like some of the abilities now to create your own ChatGPT and other types of things that exist, I think what you're seeing is you have sort of this, we have a hammer and everything we see is a nail situation, and people are trying to use generative AI for things that are better for simple algorithms, or they're better for neural networks and machine learning approaches, or any number of other things. So what are the types of situations that you found yourself in, or that things that you look for when you're like, I need to reach for building a sort of model or finding a model to incorporate in for this piece?
I was having this very same conversation. It was me, Gary Short, who I'm going to reference this quote to, because I absolutely love it, and I have to give him full credit for it. And then two or three other random people. We were outside the bar at KCDC, kind of having this conversation of why would you want to use a neural network and in what situations it's good for. And he put it the absolute best way I could ever put it, which is, most people, they look at a problem and they go, okay, well, if I need to solve that problem, I need to do this, and then I need to do this, and then I need to do this, and this will be the outcome. And if you can do that, then that's what you should do. And then there are times where you look at the problem and you look at the number of parameters you have to deal with. Whether or not all of them are useful or not is not important, but you look at the number of parameters available, and you look at all of the stuff you have to deal with, and you look at what's expected at the output, and you go, I have no idea how we're going to do anything with that. That's when you need a neural network. And you need it when those number of parameters are in the 200 plus range, right? They're using neural networks for things like weather forecasting and predicting atmospheric conditions, whereas all of the variables of what's currently going on in the atmosphere is such a huge range of data, and the amount of transformations you could do upon it to get an answer at the other side is so astronomical, you can't even begin to wrap your head around the problem. Well, that's the type of problem a neural network is really good at, because you can say, here's observed results and what happened at the end. So I have generations perhaps of training data where I can go, these conditions produced this, and you can train it on it until it can get that 90% correct. And you have no idea how it's using it. And even if you know how a neural network works, and you really went in and looked at the actual like data in the background that it used for the training and everything, you would still have no clue how it came up with the answer. That's the type of problem you need a neural network for. So it's not the, oh, well, I have this small subset of data, but if I do this, this, and this, then I can figure it out at the end. No, it's the, I have astronomical amounts of data, and I have no clue how I'm going to get to the end result.
Interesting. All right. We have more of this conversation to come, but first, let's have a brief word from today's sponsor, This.Labs. This.Labs is a development consultancy that specializes in application development and upgrading legacy systems. They've been trusted by companies like PlayStation, Capital One, Herman Miller, PayPal, and T-Mobile. Facing challenges with legacy systems and need to modernize? This.Labs has experience in enterprise migrations and upgrades, providing a detailed roadmap for modernizing your software solutions. Their engineering leaders are industry veterans with a deep understanding of modern technologies and best practices. Learn more about how This.Labs can help you achieve your goals at this.co. That's THISDOT.co. Now, let's get back to our show. All right, Chris. So now it's time to kind of dive in a little bit here. So I don't know if we should start with sort of labeling some of the elements of a neural network. So I'll just sort of leave that on the table in case that's where you'd like to engage first. But I think my broad question is just, as we need to, like in a recipe, lay out the ingredients, what are the kind of techniques and tools that we would use when we're experimenting with our first neural network models?
So you have to remember, after everything's said and done, it's a mathematical model. So the first step is going, here are the parameters I have. Here's how I can somehow mathematically model it into numbers. However you want to do that, whether it's because you're taking types of data and you're doing something as simple as like an enumeration list where this is equal to 1, this is equal to 2, this is equal to 3, whether you have some sort of observed quantitative data, which then in some way you can normalize, except first you've got to normalize your input, right? That's step one. So you can get it into the mathematical model. At the other end, you have to have, these are the things that could come out, and how am I going to take that data and turn it into an answer? So that's your step one and your step two. So there is that art of how we do that. And the back end side is actually a little easier to deal with. And we'll get to why in a moment. But that's your first step. And then the hard part, in which there is no answer and it's an art and it's mostly playing around until you find something that works, is what do you do in the middle and how many times do you do it? So laying all that out, the way a neural network works is you have all of that input data and you have at least one layer of what we call neurons in the middle. And those neurons take every piece of data from the input layer and they do something with it, and then they pass that on to the next layer. The trick is that all points in time, every layer gets every node in a layer gets every piece of input from the introduction from the previous layer, and then at the end it passes it to every place in the next layer, which is when you get that really complicated looking chart when people see neural networks and there's arrows going all over the place because everything's connected to everything, right? Or everything looks like it's connected to everything. We'll talk about that in a moment. But you get that mess of a diagram. So there is the art of saying how many intermediate layers do I need and how large do they need to be to solve the problem. Sometimes based on the problem, it may be smarter to take a bunch of input parameters, squish them into something smaller, but let it run through a couple smaller layers to get to an answer. Sometimes it may be better to just expand it and then pull it back out. It's kind of an art there at that point. But at the end of everything, that's basically all that's going on. Is you're taking every input parameter, you're throwing it to these neutrons that do one stupid, simple operation, and we'll get to that in a moment. Everything in that layer performs, and then it repeats to the next layer until you get to an output layer where you then decide what's going on. That's quickly the way it works. When you start looking at all those things, mathematically, it translates very nicely to linear algebra. And by that, I mean, you have everything.
Remember that course you took in college, everybody?
If I've said this many, many, many times, knowing now what I knew then, or if I'd have known then what I know now, if there was a class in college I wish I would have paid more attention to, it was linear algebra. So any of you who are in school, pay attention to linear algebra. It does a lot more than you think.
I'm so sad too, because when I was in college, that professor was a very eccentric one, the one that I had. And the very first day, I remember he just held up his hands and he said, between these sets of fingers, which ones are triplanar and which ones are, this. And the whole class was just so confused. It was an extremely abstract conversational one. And so I feel like I remember very little from that class. And yes, same as you, I was really sad when I realized that was the one class I really didn't need that professor for.
Yeah, mine was almost a similar experience. Our professor was actually a manager on the International Space Station project for Boeing, who was just an adjunct that came in to teach the class. And so all of his examples when he started doing things were all like how they would use this for the transforms to move the solar arrays for the International Space Station. And I just glossed over because that I didn't care about that. And then I started getting into real world mathematical applications and computer science. I'm like, oh no, this was all linear algebra. I made a huge mistake. So yeah, I'm the same way. So, but to get back to the point, so all of that input stuff, that's just an input vector. It's a one-dimensional list of items, right? It's just an input vector. That stuff in the middle, all those lines that go to all those neurons, that's just a matrix because we're just saying when this item comes in, this is the weight when it comes over here. So now you have a vector and a matrix, and we can very easily do matrix manipulation or matrix multiplication on that and produce another vector. And then that vector becomes what the actual sometimes you'll see neural networks that talk about also having biases. The biases then get added to the result of that multiplication, and then that's your input parameter to the neuron. And then the neuron will generally perform one small, easy piece of math on that value to normalize it. And then it repeats to the next layer through. So it's all just a huge linear algebra transformation, which is why AI is using graphic cards so much, because all computer graphics is matrix manipulation. It's technically array manipulation, but it's matrix manipulation on that the screen is a matrix of the colors of every pixel. And as the graphics card runs all the shaders and does all the manipulations, it takes the input vector, it very quickly and parallelizes saying, take this input vector, run it through this function to produce this pixel, and it transforms everything and it repeats it over and over again, which is why it has thousands of cores that are very efficient at doing one thing, because that's all a graphics card is doing. But that's also why these graphics cards get used so heavily by AI, because it's the exact same thing. You're doing a matrix manipulation.
So when you're walking people through this introduction of how to create these neural networks, are you focused on helping people understand how to write the code that executes kind of like these matrix manipulations? Are you helping them understand how to begin to develop one of these models, like decide those weights and things like that? Or is it both? Do people need to learn both of those things, or are those two different things to learn? The implementation.
So
and
when
the
I do it, I actually teach
refinement.
people what they need to worry about. For example, we talked about that big matrix of weights and that vector of biases that go into. You never want to try to guess what those are.
Fair.
If you look in my demo code is on my GitHub, so maybe we'll get a link to that somewhere. But if you look at my demo code, when I initialize the weights and the biases for the sample code, I literally call a random number generator. It's just a random number. And I tell people, hey, go change that function that does random and have it set like fixed values. And you'll notice how quickly the network will not converge. So if you really knew what you were doing and you knew certain tweaks of the data that you knew were going to be important, like let's say you knew a certain parameter was useless, but you wanted to throw it in there anyways, just in case the computer found value from it. Yes, you could manually deprioritize a certain value or something that way. But for the most part, you don't know how it works. You have no guess how it works. You don't care how it works. You just want to initialize it with random data and then start telling it when it's wrong, how wrong it was. So the real emphasis is here's what's actually going on in the magic. But what we really care about is here's how you treated that input layer and here's how you need to treat that output layer.
It's really fascinating because, and maybe we'll add this to the show notes as well. I was looking at a video that had a great representation of this, where they showed some sample data on a graph, and they color coded it based on whether the true value or the true result needed to be good or bad. And they started tweaking all the weights and the biases, and then they showed an example where they had multiple sort of layers and the effects that having multiple sets of weights and how it bent the model. And it's totally fascinating to start to develop a mental image of kind of exactly what you're saying. Like, you're not going to be able to look at this and guess, but that you can sort of get an somewhat intuitive understanding of what's happening there. Like, it's fluctuating that classification system. And the more layers you seem to do, the more complex the shape is that it can cut into a graph, basically, of data, which was sort of a fascinating sort of visual representation of like exactly what you're saying, how hard it is to decide what these weights are. Like, you'll never be able to just sort of look at, even if you could look at exactly what reality was, you could never just go, oh yes, I know what this is.
Right. And in the talk I give, in the slides are also on the GitHub, so that reference is there, which is why I'm bringing it up. There is a link to a playlist from YouTuber Three Brown One Blue, or Three Blue One Brown, that did a entire series on neural network. He's actually where I got the idea to use the vector or the matrix manipulations as a way to help people wrap their head around it. Because I had never before then saw that, oh, I've seen this classical model and I knew in the background I was basically doing matrix manipulations, but using it as an explanation tool had never occurred to me. So full credit to him on that one. But he's got something where he sets up this neural network in the thing, and he says, here's my input, and here's how I arranged my input, and here's what I imagine this first layer is doing, and here's what I imagine the second layer is doing, and here's my output. And he goes through all the training. And then at the end, he actually shows, based on what he imagined it was doing, which was like, we only care about this small section of the image, and then is this small section of the image fitting what's actually going on? He actually then shows what each side is doing, and it is, you can't even look at it and pretend to know what's going on with the visualization he gives. And I love the fact that he does that, because it's like, I imagine this is what's going on, and I can even hand set up the initial weights and biases to make it do this. But then having said that, after it's figured it out, and this is a fully trained generic neural network, you look at what it's actually doing, and it is not based in reality whatsoever.
Simultaneously, the coolest and scariest part of the whole process, that
yes,
we sort of can understand everything to a point, and then it exceeds us, and we hope that we pointed it in the right direction before it sailed off beyond our comprehension.
Yes.
So so if this is kind of the first step, so we kind of set up these, as you sort of described it, the code-centric version of these matrices and these manipulations and the ability to manipulate these weights, that was more than just one step, but what is the next step in the process of implementation? Is it to refine it based on data? Like, what is next then?
So to hit that, let's actually talk about how you actually train.
Okay.
Because it is actually 10 times more complex than using one. And the way I put that is, if you could name anything in math that's really hard for a computer to do, what would it be?
I'm not sure. What is the hardest thing for a computer to do?
Calculus, because it's really hard at continuous operation.
Yes.
Right?
Yes, non-discrete operation.
All of forward propagation, which is how you ask a neural network to give you an answer, is linear algebra, and it's a floating point math, but it's all just simple math. Mm-hmm. All of training is calculus.
Okay.
So that's where the trick really comes in. The results you get out of a neural network is, you say, here are output nodes, and what you should be trying to do is, it's a probabilistic structure of it saying, I am 90% sure it's this, I'm 30% sure it's this, and it basically guesses based on the parameters what the output would be. And then based on that, you can say, okay, well, in the simplest way, it's supposed to classify between these 5 things. It's 90% sure about this. It is less sure about everything else. So the answer is that. Right? That's how it works. At the end, after all is said and done. Well, when it comes up with wrong answers, you want to be able to say, no, it was wrong. And so what you do is you say, this is what you should have come up with in the ideal case. So let's say we're passing in an image of a number, because this is a classical neural network example. You're passing in an image of a number, and then you're telling me at the end whether it was the digit 0 through 9. It was supposed to be a 3. It came up with an 8, let's say, because the numbers were too close together on the curls. So you say no. So you say, no, what I wanted you to give me was 0% chance for everything but a 3 and 100% chance for a 1. And then you use that to say, now go back and figure out, if this was the value I wanted and this is what I actually gave, how wrong was it? Push that back when you say, how much did the pieces that came into it contribute to that? Tweak them and slowly but surely work your way back in a mechanism called backpropagation. And it is the most complicated part of the entire process. And the reason is, the calculus behind it is what is known as a gradient descent, and it is minimizing the error function on the network based on a gradient descent. And I know I said a bunch of things that if you don't have a degree in math like I do, get really complicated. But the idea is, let's say you have your simple X and Y curve, and the X and Y, the normal graph you're given represents the error on the function. So you want to find the lowest point in that graph, absolute lowest point, right? Because that's where the error is the least. So you take the point you're at, which you can very easily calculate, and then you say, based on the slope of where you're at, I need to slightly go down. And you start to nudge it down until you can hopefully find the bottom, hopefully not getting stuck if there's like a little peak and valley in an incorrect valley. It's called a gradient descent. Don't worry too much about that, but that's what all the calculus is doing. If you've ever taken calculus, it is a minimization. It's looking for the global minimum on this function. That function is the error for the overall network. That's really easy to describe and get somebody's head wrapped around if you have sufficient visual cues for a 2-dimensional or even a 3-dimensional graph. Because as humans, we can very easily think about it in 2 or 3 dimensions, right? Mm-hmm. We are passing in hundreds of parameters into this neural network, and we're probably asking for hundreds of possibilities at the end. Even let's say we're even only asking for like 10, right? We're doing the digit analysis. So we're asking for 10 parameters in the end. That still then puts that nice function we were trying to describe in 10D space, and it's really hard to wrap your head around without the pure mathematics. So this is where the complication comes in. But yeah, basically to train it, you say, this is how wrong you were, now go fix it. But then you don't do it per sample, because then you get it really good at figuring out that one example. I can't remember the exact name for it, but you can overtrain it to a certain example to where it has a bias to where it will always answer that. It gets really good at solving that one problem, not the generic problem. So you do that for a huge batch of sample inputs that you have the answer to, and then you basically average the nudges that got wrong, and that's your little move. And then you do it again, and you keep doing it again until that error function gets as low as possible. And that's when you start talking about how it takes so long to train a neural network. And that's if you're doing the most optimal mathematical. There's also other algorithms you can use to train neural networks that work great if you don't know how to give it the correct answer. But then they take much longer because now you're working on way weirder techniques. And when you were talking about genetic algorithms for training a neural network is another example of a training algorithm. It's a training algorithm when you can't necessarily prove an exact, this input should be this output. You just need to say perform. The one that performed the best is then going to genetically move on to the next generations, and the ones that perform the worst are going to get thrown away. And then based on the ones that perform the best, we're going to create some new attempts at it. And you literally, like the process of evolution, do it over thousands and thousands of generations until it learns naturally.
So I think people will be equal parts amazed and excited listening to this, but also a little scared. And by that, what I mean is we're talking about all these things that they have to train and they have to confirm and they have to see these things. But when people are doing that, if people leave here and they want to start playing with this, they're not having to code the parts that we're talking about that do these back propagations, that do these kinds of analyses, right? Like what we're talking about is using tooling that exists. So like people can make fully custom models, but they would do it inside of like a harness or a tool or a ecosystem that exists to kind of help facilitate this. Is that right? Like what are examples of some of the things that people would be using or they can look into to play around with this kind of stuff, to kind of see how this these ideas work?
Yeah, nobody wants to program one of these things. Well, I mean, people like me want to program these from scratch, but your average person doesn't want to program one of these things from scratch, and you absolutely should, right? That's heavily into research type R&D type of people who really want to wrap their heads around those types of problems. But as far as just being able to use one, it's a simple, and the libraries will do it for you. You basically say, hey, I need a neural network, and you say, here's all my input data, here's all the examples I have, and here's what I know based on this example the output should be. And it figures out how to divide up the data and how to do all that training for you until it can get that training data to a high enough percentage of correctness that then you can start throwing unknown data at it, and it should produce a correct result. They recommend, unless you have an extremely closed problem. Of course, if you have an extremely closed problem, you probably don't want to use a neural network. think of image classification. That is not a closed problem. We always produce new images. So that's an example of an open problem. A closed problem is where I have these inputs so I can have a finite number of, a very discrete number of ways they could combine. And I could literally write something that exhaustively went through every one. If you've got a closed problem, it's probably not the best thing because then you can end up overtraining to a problem. Not to mention, you could probably, given enough time, find an algorithm that would produce the result, even if you had to program in exceptions to 100% more so than with any sort of neural network or any of the other machine learning algorithms, probabilistic algorithms. You're going to get within a degree of correctness, and you try to get that degree as high as possible. ChatGPT ain't perfect because it's not, if nothing else, it's not trained on the newest data. So it may give you an answer which was correct at the time, but has later been proven false.
And I mean, that's the hallucinations too, right? I mean, like it's just part of any probabilistic anything is that
right.
There's a percentage chance it's going to go catastrophically wrong.
Right. So, if you just understand that, hey, if I have, this is an open problem, but I have 3,000, 10,000 data lines where I can say, this is the input data. Don't know if all of it's needed or not, but this is the input data we have. This is the output. Then you've got something that's a good candidate for training. And at that point in time, you can just tell the computer, hey, here's my input parameters. Here's what I need my output parameters to look like. I think it's going to need 2 layers. Like you can give it a couple parameters and let it try to train. It sounds bad, but I mean, I've thrown enough hardware at the problem, it can do it quickly. But I mean, even on like the laptop I'm using right now, if I had like 3,000 input rows and I wanted to train a sufficiently large neural network, let's say there were 10 parameters, it could probably get through it, let it run over the weekend while you're just spending time with your family, and you'd have a first hit the next day or at the end of the weekend, and then you could tweak around with some things and play around from there, because it's gonna take that input set. It's gonna say, okay, well, give me 2,500 of them. Let's train it on that, and then we'll see how that result goes against the other 500 we didn't use. And then after it uses that to train the network and get closer, it'll then randomly, exclude this 500 for the check at the end. And it will do all that stuff for you based on best practices. You don't have to know all that stuff. You don't have to know the calculus. You don't have to know the linear algebra. It's just the idea that if you're comfortable with the idea of what's going on behind the scenes, it may help you model the data in a way that's more useful to the tool.
One of the things which I think would be useful for people to hear about if you have thoughts is this idea of sort of bias that people should, introduction to bias, not in terms of what bias can come up. I think some people are familiar with different types that have made the news of types of bias, like certain detectors that work well for people with white skin tones, but not with black skin tones. But I think that there's even other types of bias, things like overfitting a model and things of that nature that people can unwittingly fall into, even if they're trying to be careful. So as people sort of play with this, maybe for the first time, do you have any advice on things that they should be looking out for or asking themselves or looking at when they're building a model to make sure that it doesn't work perfectly for history, but fails for anything that will come up or anything of that nature?
Yes, that's a huge issue. And this is almost out of the realm of computer science, and we're now into ethics, because these models do a really good job of figuring out and classifying the data you put into it. However, if the data has implicit biases in it, it's going to learn those biases. And there's not a good answer to this question. Especially, we tried to, there's infamous things where banking industry has tried to decide whether or not to allow a loan based on these parameters. And then they realized it was supremely biased because the bias of the people they're using the historical data from had these racist bias, and they were using the same racist bias as an input parameter. So now it explicitly has that bias. Okay, well, let's strip out this factor, which was this racist factor it was using in the past. Well, it still ends up coming up with that bias because somehow amongst the data, it figures out this combination of things. Like, let's say someone who is slightly in a certain geographic area, someone who is making this type of salary compared to this type of salary, it can then find those other biases that contributed to that in the first place, and it will still end up programming in those biases. The way you do it is that you find examples that don't have that bias that was built in the first place, and you remove them. But even then, now you're still, again, huge ethics question of how do you correctly deal with these biases that the data inherently own. And again, that is not a mathematics question. That is an ethics question. That is another 3-hour debate.
Yeah, yeah. Well,
But yeah,
that's on
that is something you have to pay attention to, is that if you're not dealing with something purely quantitative and there was any sort of subjectiveness in it, that subjectiveness among these were the parameters, this is the result, are going to inherently go into the system you're creating.
Yeah, and I think like that's I think the most obvious ethical piece of this, but even on a correctness level, like I've heard that you might have, say, 1,000 points of training data, but maybe it's the case that your data has a fuzziness to it. So for example, I remember hearing this story about around sort of Nate Silver and the types of people that do like elections forecasting. And there's this idea that that data is very probabilistic by nature and it's very fuzzy by nature. And that if you can train a model that can perfectly guess exactly the winner of every election that's already happened. But it turns out that very few of these are very good at predicting future elections. And it's just because the world shifts, it changes. There are anomalous events. And I always think that that's fascinating, this idea that sometimes the data you have in your training set, you may or may not want to include it in the result if some of that data is a bit anomalous, because it gets this perfect training. And I think what the part that I'm really confused about, and maybe that's just the art, and that's why some people get paid a lot of money to do this stuff, is like learning to identify that when already you've sort of said that this is a complicated, not an unknowable complication, but like these things advance beyond our capability to just check the math on sometimes. So this idea of like, how will you know this? I think is like you said, an ethics and a responsibility question, but certainly a technical challenge, and maybe even a little bit of an art at the base level of it as well. And I think maybe that's part of the exciting part of it, but certainly one of the challenges of it.
Well, it not only is it one of the exciting parts about it, it's one of the scariest pieces about it. Because let's say you even had the conversations with the correct people and you tried to identify all the things. And let's go back to the voting thing you have. Guessing who's going to win an election based on a small time exit poll is a very difficult thing to do for many factors. One, you're using historical data based on trends of a geographic region, but a presidential election happens every 4 years, in theory. The entire demographics of that region could shift during that point of time. And I don't even mean if something really weird happened. I mean, a certain, historically speaking, the older you get, the more conservative you get, the younger you are, the more liberal you are, historically speaking. We're just going to use this as a broad paintbrush stroke.
Sure.
Yes, I know I'm adding to the bias by saying this, but I kind of need something to base the point on. We have these models based on this region that this is the way people generally think. However, over the course of 4 years, a certain percentage that may or may not be measurable based on changes in medical conditions or maybe a catastrophic event that happened, a number of those conservatives at the top are going to roll off because of death. Or maybe just they have no way to get to the polling place at the time. Let's say they're recovering from surgery, they had no way to do it, emergency type stuff. That version goes away. And there's a newer section of what should be considered more liberal people that come into the pipeline because they become old enough to vote. So if nothing else, those demographics are hugely changing between where your sources of data are from, which is why elections are so notoriously difficult to judge. They try to say they have the models where for a general demographic region, the age groups where the transitions between more liberal and conservative happen, and so that's why as people roll up the top becoming the bottom, they can keep the numbers accurate, but they don't know. And it's just throwing data at the wind. Any sort of, I don't want to say any sort, there's a couple of small counterexamples. Any sort of machine learning algorithm that is currently used, typically speaking, is a statistical model. There are a couple that don't use pure statistics and are just pure probability. That's why I said there's a few outliers out there, but they're statistical models. And as we all know, there's been books written about it. You can prove anything you want with statistics if you try hard enough. But if you wanted to prove something one way or the other, even with a large statistical model like a neural network that's taking thousands of inputs and doing that type of analysis, you can still choose your data of what to put in it to get the answers.
Yeah. I mean, hey, there's a whole website that has fun with this, the whole spurious correlations, the correlation versus causation stuff, you know?
Yep.
You could build a model that is very accurate for certain things, but is obviously laughable on its face. And that's the challenge. That's the challenge that's put in front of all of us as we approach these models. So we are wrapping up here. Chris, can you give people an understanding of kind of where they could find you online, or if they're curious about getting into this now, inspired on this, that where they can find out more, or maybe?
I generally can be found anywhere online at Freestyle Coder. I've got Freestyle Coder at Twitter, Blue Sky, Mastodon. My GitHub is Freestyle Coder, et cetera, et cetera. The one place I couldn't get was YouTube. So YouTube, it's at Chris_Gardner. It's amazing how many people try to use that handle on YouTube that I can't get with. But also, if you go to my GitHub, which is github.com/freestylecoder, there is a project in there called DIYNN, Do It Yourself Neural Networks. I use that as a link because, one, it's got a couple of the visual aids I use. When I give that talk, it's got the source code in C# of a neural network you completely pull down, play with, start playing around with things, see what's going on. But then the slide deck's in there as well, which includes some resources like to that three blue, one brown video I talked about, some other resources that kind of really break down the math that's going on. Things like that. So those are some good places to kind of learn what you need to look for as you're getting interested in the journey. And of course, I'm available anywhere.
Wonderful. And we will make sure to put those links in the show notes so you didn't have to rewind this to take notes. You can grab the links from down below. But that is going to be it for us today. Thank you so much for listening to this episode of the Modern Web Podcast. Thank you to our guest, Chris. As always, we say the conversation does not stop here. As you heard, you can find Chris on Twitter at FreestyleCoder. That's FreestyleCoder. You can find me online at RoboCell. As for the podcast, you can find us online at moderndotweb.com or on Twitter at modern.web. And as we close out, we'd like to thank our sponsor, This.Labs, one last time, who would like me to remind you that you can approach your most pressing tech challenges with confidence, leveraging This.Labs' tailored development strategies. Trusted by industry giants like Meta, Google, and T-Mobile, they specialize in bridging business and technology gaps, modernizing legacy systems, and ensuring sustainable application architecture. Discover how This.Labs can empower your organization at this.co. One more time, that's THISDOT.co. Thanks, everybody. See you next time.